well, I guess it's review, right? Oh, yes, that's not so good, but it'll do. Well, I can tell you what's going on, and this will be part. So we'll go through a review today. I thought your performance last time was great. It might have been helped by the fact that we pointed you a little bit in the right direction, but you largely did it yourself, so kudos to you for that. May not be quite so generous this time in terms of directing you very specifically, but we'll certainly get partway there. As in previous times, 3 questions. Each one is 110. You get to bank the 10% overall. 3 questions are on the 3 areas. One is on pipes, pipe flow, Moody Chart, friction factors type stuff. We've covered the stuff you need for that, but certainly we'll talk about pipes this week, and you might also like to ingrain in what we'll talk about this week into what might be used for that, just in terms of background. But certainly you can do it in stuff that is the cutoff on Friday, 3 days ago. One question on the energy equation, and one question, as if you've looked at any of the prior exams, this ubiquitous question on dimensional analysis, getting you to go through the characteristics. And so those are the topical areas, which I think also sit in with 8, 9, and 10, I guess, in terms of our week's worth of classes. They draw slightly on other things from behind, and I'll, previous to that, and I'll make a point of exactly what those are. So like last time, I'll certainly give you an equation sheet that includes everything you need, and you know that that's not the whole show, right? You need to know how to use it in creative ways. And so having the equations isn't necessarily the whole deal, but certainly we can talk about that. Okay. Any questions before we get rolling? Okay. Hopefully this will work okay. It seems to have a lag attached to it, which I don't like very much, but that's okay. So in terms of what we've talked about before, let's call that... Oh, this is horrible, isn't it? Well, fine. What properties do you need? Let me be very careful. This is perhaps good for you. You recognize that, I hope. Ideal gas law. Of course, you all know that. You know that you use absolute temperatures and pressures, and you get densities out of it. You know Newton's law of viscosity. Shear stress is proportional to a constant called viscosity, dynamic viscosity, times a change in velocity in the x direction relative to distance in the y direction. Velocity orthogonal, the change in velocity as you go perpendicular to that velocity. Bless you. And of course you know Newton's other important law, which I'm not sure you need, but you certainly know it. So those are the previous components. You also have in your arsenal conservation rules. You certainly know that density times area times velocity has to be conserved between upstream and downstream. You can thank Steve Jobs or whoever's successor is that we're using this. I think it's something that in the new operating system it doesn't work. If I use the previous version of Skim, it allows me to write, but then it disappears. Then you write the next thing and that disappears, so nothing actually shows up. So I guess at some stage they'll rectify that. So we know conservation of mass. Sometimes we use this to be able to close out the Bernoulli equation when we need an extra variable, and you certainly know that from what you've done. It's really just a statement that comes out of this slightly more comprehensive term, which you don't need, but I'll write anyway. which is the, a regular conservation of mass statement. Don't think you need it, but you know that mass is out or positive, mass is in or negative. Momentum. Linear momentum. You do need mass times velocity. And in its very simplest form, it is that velocity multiplied by mass flow rate is equal to sum of the forces. These are vectoral quantities, but typically we usually just write it in terms of one resolving in one direction. And same applies. Mass flow rates are positive out, negative in. Velocities are positive in the global coordinate system. Forces are in the global coordinate system. So we've used that in the past. So those are the historic components that you need. So energy, which is what I'm writing here, if you can make that out. I'm doing my best. So energy, you know that the energy equation comes in two forms. It comes in one form that's kind of useful to us in talking about thermodynamics, that hated subject, much inferior to fluid mechanics, of course. And you know that when we write that, joking of course, that it's written something like this. Enthalpy, which we used, I guess it's out, right? Minus H in. Yeah, horrible, horrible, horrible. A half, that's a 2. V out squared minus V in squared. This is, look, apart from horrible. Plus the elevation term, gravity times Z out minus Z in. And those have to equal thermal work, Q net in, I N, and work, mechanical work, shaft work, I guess. So we don't have to worry about this sign convention on mass flow rates. Mass flow rates, it's in a streamline basically, right? It's upstream to downstream. And so we don't worry about mass flow rates. Mass flow rates is a scalar, a positive scalar. I guess enthalpy, we know, is the sum of two components. It's internal energy per unit mass plus pressure divided by density, I think, right? Yeah. So enthalpy, which is H, is internal unit, internal energy, which you can't make out there. I'll start again. In, t, It's internal energy per unit mass. I'm not going to write it out. This takes too long. So what do you have to remember about this? This is positive if in. This is positive if you're putting work into the system, pumping. It's negative if you're getting work out of the system. So the sign convention takes care of that. And you see that this has the same terms. It's written between in and out. So it's written specifically between upstream and downstream, as we have talked about in the past. This is the inertial term in Bernoulli. This is the potential energy term in Bernoulli, and the pressure term in Bernoulli comes in here. But it also has this extra internal energy if you want to do calculations about chemical reactions in systems, and we used it in a couple of examples. we used it historically in a couple of examples in the videos that you looked at in online. Okay, so that's one form of the energy equation. So I'll try and keep both on here at the same time. The other one, which is probably much more useful to you in the things we've talked about, and we always write it in terms of just lengths, elevation plus pressure head. You sound like me. I think I'm coming out the other side of it. Cough, that is. That's not J, it's G. Plus pump head. Definitely need to know this equation because it's kind of the underpinning of what we've talked about so far in many things. Pressure head, velocity head. Apologize for the, I'll try and, didn't realize there's such a lag in all of this. Squared, of course, plus sum of major losses and sum of minor losses. And so obviously it looks similar to this. It's between upstream and downstream, inlet and outlet. We know that because now non-recoverable losses are written in this, this absolutely has to be upstream. Won't, I can draw, it's easy for me to draw a stream tube, right? This has to be downstream, this has to be upstream. The velocities are streamlined velocities. It doesn't matter whether they're in or out, but this has to be 1, obviously, and this has to be 2. Pump head we define as being power, which I've used the terminology W dot. Work is Newton meters. Rate of doing work per second is power, watts. Named after that delightful Scotsman. And it's divided through by, you can write it in different ways, unit weight of the fluid that you're pumping, multiplied through by the volumetric flow rate. We've always used Q. And of course Q would just be equal to what? Velocity times area. Or equivalent. Q1 would be that anyway. So whatever Q is in the system. I guess it's important to realize that Q would be whatever the flow rate would be in the system, not necessarily at 1 or 2, but actually if it's steady state, then the flow rate through the system has to be the same as the flow rate at 1 and 2, right? Otherwise you'd be accumulating stuff. So that is true. I say that because when you deal with these terms for the head losses, we know that the major head losses are due to this expression here, which we spent some time in the last week dealing with, a friction factor. The drop occurs over a length of pipe of some given diameter as a scaling dimension, and a velocity head. And it's important to note that this velocity is the velocity in the pipe, not necessarily at the nozzle, where it might be different, but it's in the pipe. So this is whatever V is here, and you can think of this being delta P, and of course HL is really equal to what? Delta P over gamma W, right? Gamma, whatever the fluid is. So you can think of this as being this. So this is the amount of irreversible loss that you get from driving flow through systems. It's due to the fact that you have shear stresses added along the side of this, which must counteract the flow. So in other words, the pressure upstream is larger than the pressure downstream. That energy, that potential energy in the system, is eaten up by this viscous dissipation, just like me pulling my bag across the table. It uses up energy when it does that through heat, and it has to be resisted against. The minor losses, because they're in fittings, so in other words, this might be our pump head that we have in here. We've talked about flow in systems, maybe that look like this, between 0.2 and 0.1. Then the losses that occur within the summed units of these pipes, which we talked about on Friday, these are the major losses, which are given by this. The minor losses, because they are discrete, occur at bends and fittings, etc. And because they're discrete, they're not defined over any particular length. They're just defined as magnitudes of loss by a single coefficient, usually called K sub L, loss coefficient, but multiplied by the same term, V squared over 2G. And just to reiterate, these velocities are not velocities upstream or downstream, but they're velocities in the fittings by definition. And so we deal with things that way. And this would be HP, of course, whatever. These relate to, especially to the Moody chart. Which is an important concept for us. If you need one, you'll be given one. But we've talked about it in generality. So I guess we can do it. I'll put it up here. Mr. I guess it's Mr. I don't know for sure it is. It's 1800s. I'm guessing it probably. Well, actually, that's not necessarily the case. Moody chart. Not Clark chart. I'll do it backwards H. All right, and what are the features of a Moody chart? It allows us to calculate behavior as a function of two parameters. Actually, is it worthwhile? Yeah, we'll talk about that later. So we mentioned when we talked about dimensional analysis that there are three characteristics. You want to have a model that's exactly the same dimensions. So length similitude, length over diameter is one of the terms in that. Relative roughness is one of the terms. We want it to be flowing in the same regime. So Reynolds number is the term that classifies what's going on. So we want our calculations to be at the same Reynolds number. And if we do that, then we can calculate what the Euler number would be, which would be either the fluid pressures on a structure or the frictional drag within inside the pipe in our particular case. And so when we deal with pipes, Moody chart gives us a chart that links Reynolds number, classified for a pipe as a function of the velocity of flow, the density of the fluid that's flowing, and some characteristic dimension, which is always the diameter of our pipe, divided by the viscosity of the fluid. We've kind of drawn a picture of what our pipe looks like before. You've seen this many times, right? It has some characteristic length, but that's not the unit that we use. It has some characteristic diameter, and that is the parameter that we use. And it also has some characteristic roughness attached to it. And we call that epsilon. And we know that the head loss universally in this expression is equal to some friction factor, a scaling of how long the pipe is relative to its diameter. Clearly, if you double the length of the pipe, all things being equal, you double the resistance. You quadruple the length of the pipe, you quadruple the resistance. Hence, that would change. And it scales with the velocity at which it's flowing. So this Moody chart, of course, gives friction factor as a function of these behaviors. We talked about three regimes. We talked about fully turbulent, one way to get me to slow down, I guess. We talked about laminar. And we made the analogy that laminar means like taking a pack of cards, which are laminae, and scooting them across each other so that the velocity are all parallel to each other, so there's no turbulence in the system. As you increase the flow velocity, all of a sudden you start making eddies, and you move from this behavior at about 2000 to fully developed turbulent flow at 4000. And the behavior within each of these regimes is that in the laminar regime, the friction factor is a function of Reynolds number, and maybe geometry of the pipe, whether it's circular or not. So I'll call this geometry. So I'm trying to write geometry. So anyway, so this relationship clearly is an inverse relationship with Reynolds number, it isn't increasing. And in the turbulent regime, the friction factor is principally a function of relative roughness, epsilon over d. In this curve here, there's a curve for a smooth tube that comes down here. So this is epsilon over d equals 0. By definition, epsilon 0 means smooth, dead smooth. And these individual curves here are for different values of relative roughness. So this is for relative roughness large. And it gives a larger number of friction factor. Friction factor increases upwards. And these are values for epsilon over d progressively smaller. And the reason that it's really only a function of relative roughness is that it's horizontal, right? It's horizontal as a function of Reynolds number. So in other words, as you increase your velocity of flow, the frictional coefficient doesn't change. This value doesn't change. The velocity will change, so there'll be more head loss as you're driving at the higher rates, but the friction factor doesn't change. In this regime, as you increase your velocity, the friction factor will actually change in response to your behavior. And so that's an important consideration, I think, in what we're dealing with here. Okay? How are we doing? So that's pipe flow and how Moody charts fit into that, a badly drawn Moody chart in that. And so the only other part, which we've actually used to explain pipe flow as well, is dimensional analysis. So we developed the Moody chart equations kind of from dimensional analysis, which of course is one way to develop them. And I suppose that the three cardinal components of dimensional analysis are the ones that we perhaps alluded to before. You could probably almost guarantee there's a Buckingham Pi problem if you just look historically. So dimensional analysis. dimensional analysis. And I won't go through Buckingham Pi here, but we can look at that in a second. But I will say that the three components I think that you know of in terms of getting solutions in dimensional analysis are one, to satisfy similitude, which is geometric. Jeez. So in other words, the model that you're looking at, if this is the model you're looking at, it has to look like this in microcosm. All dimensions have to shrink by the same amount. That's all it means. So in other words, it has to, if it's a matchbox car of a Lamborghini, it has to look like the Lamborghini if you imagine it being squeezed up. So in other words, in our particular case for pipe flow, our exposition of that is L over D. So ratios of dimensions. The length of the pipe to its diameter, they have to be in the same ratio. They don't, but those magnitudes of D don't have to be the same if you're doing it. The second requirement is kinematic. Which means that the Reynolds number for the model has to equal the Reynolds number for the prototype. So if you're using it on a building, you've got a model of the building, the flow around the model in the wind chamber has to be the same Reynolds number. What that physically means is that the flow patterns around the system are identical in both model and prototype. It doesn't need to be the same fluid. It could be water on a model, and it could be air on a prototype. So long as the Reynolds numbers are the same, the eddies around them and the structure of the flows will be identical. And if the structure of the flow is identical, then it will also then satisfy this final requirement in that the dynamic similitude is also met. And that is that the Euler numbers of the model and the Euler number of the prototype, and you remember that that should be a U in there, but don't worry about that. Remember that what is Euler number is something about the ratio of pressure embodied forces to velocity or inertial forces, rho v squared. P over rho v squared are equivalent between the model and the prototype. And so if you measure the pressure on the model, the wind that's pushing the building over, you can figure out exactly what that pressure would be on the real system, which you'd like to maybe design for. And so that's the only issue about dimensional analysis. You can use Buckingham Pi to get these variables. It doesn't always have to conform to this set. This is really for fluid mechanics problems, but dimensional analysis can be used in a much broader system of equations than that in solid mechanics. If you use Buckingham Pi, if you use different, we'll talk about that in a second, if you use different dependent variables and repeating variables, you'll get different dimensionless variables. And so typically, not typically, but always in an exam, you'll be told which ones to use because you get a unique answer based on that. And that's purely for grading as much as anything. So those are the things that I was going to mention. We start off by saying there's not an equation you'll need that isn't on these three pages right here. I don't think. So, okay. Should I just go through? Any questions, I guess? I plan to go. I uploaded a second sheet online, which is this. So this is up on the resources page if you want to grab it. I will also make this. I'm not going to write so much on this, so I guess it might not matter so much. No questions? Okay. So we've gone through this, so I won't go through this again, but I'll see if there are any things that stick out as we go through this. Don't need that. Don't need that. This is the equation we mentioned, which this is here. And yeah, I guess it's this, right? So certainly this is fair game, I guess, in terms of what we've talked about, and we just talked about it. We did some examples online in terms of internal energy changes within a system and how steam turbines work, and different velocities out versus in this particular case, because of chemical work being put into this, because the densities are changing. Did an expression with pumps, just right. So this is one expression where this relationship would apply, because we have enthalpy defined in terms of internal energy and also fluid pressures within the system. And so you can solve in terms of that. If it doesn't involve enthalpy, it's probably pretty safe to presume that it will, the equation you probably need to use is probably more akin to this, right? Our exposition of Bernoulli's equation. And so this is just writing Bernoulli's equation. Big tank assumption, you all know that, right? Big tank assumption, so you can get rid of these velocities. You can define the losses within the pipe in some way. You can define the pump equation in some way, here defined as a function of flow rate, and solve there for the remainders. So we went through that, and so I'm not sure we have to do that again. This is an important part of what you may do in your lives, but it might not be an important part in this exam. And so you can take that for whatever it is worth. FlowNet is an incredibly powerful method. It relies on this idea of stream functions and streamlines. Fluid can't cross those streamlines. The basic idea is that if you can draw a rectilinear grid that represents your flow system, which you can do in about 2 seconds to represent flow through a dam, underneath through a wall, whatever, then you can immediately calculate the flow in the system by doing a couple of things. Having this net have 45-degree angles in it and be roughly equiax, so these are squares rather than rectangles. And if you have that and you know what the head is upstream and downstream, and if you know what the hydraulic conductivity in the system is, and you know how many stream tubes, which in this case is equal to 1, 2, 3, 4, and if you know how many drops you have to go from upstream to downstream, which is 1, 2, 3, 4, 5, 6, 7, 8 to 9, then immediately you know what the flow rate through the system is. So it's a very powerful technique. It's applicable to many of you, certainly petroleum engineers and environmental systems engineers, but and that's why we talk about it. It relates directly to the ideas of stream potentials. It's a use of stream potentials. But having said that, I said what I said, and so you can figure out whether you need that or not. Dimensional analysis. We talked about the use of Buckingham pi. I can say something a little bit about that. We already talked about geometric models, that the geometry of things should be the same. Kinematically, Reynolds number in terms of some characteristic dimension, diameters of pipes, diameters of satellite dishes, diameters of water towers, etc., has to be the case. And that if we have geometric similitude and if we enforce kinematic similitude, then we can measure Euler numbers, because we know that if both of these are enforced, then by definition dynamic similitude will also be enforced. And if dynamic similitude is enforced, then we can use the model-based pressure to be able to calculate the prototype pressure. But Buckingham pi is one formal way of being able to calculate exactly what the number of groups would be. We messed around with it for a number of different systems. We could use it for flow within a pipe. I guess we did make the point, and I think an important point to make is that if we're looking at flow within a pipe, or flow within or around a capped-off pipe, not doing a very good job here, where in this case obviously flow is at some velocity in here. In this case, flow is at some velocity around here. They both satisfy this issue that we have drag applied on this system, and we have internal drag applied on this system. And when we look at in-pipe flows, the whole essence of the problem is figuring out what this pressure loss is, because you want to dimension a pump for it. We don't care really about the fact that that pressure loss is manifest as a shear stress or a drag force, but it is, and we'd have to hold that pipe in place to stop it moving on us. Just as if we wanted to hold this tube in place, we'd have to apply a force to be able to hold it in place against the fluid that's going around it. The fact that the fluid's going around it and the shear stress is on the outside as opposed to the inside is immaterial. But they both would have this viscous losses. And that follows also when we talk about free surface flows. I think we drew these geometries together. And the only difference between pipe flow and free surface flow is that the pipe might be half full. And if the pipe is half full, then pressure cannot be driving it from upstream P1 to P2. Bless you. Because the pressure would just circumvent the flow by taking the easy circuit and going through the air with low viscosity rather than flying through the water. And so the only thing that's driving flow in this case is gravity. And gravity, as it would go downhill, will only drive it if it's tilted. And also there'd be a shear stress acting on this due to gravity. And this shear stress will be resisting flow. It means it won't go at infinite speed for a very small gradient. And so this drag on it will actually condition the flow velocity within the pipe, which is what the essence of free surface flows would be. So we introduced pipe flow using dimensional analysis. We know that for dimensional analysis we have to do a couple of different things. We can figure out how many dimensionless groups are made up by looking at how many variables describe our problem. Flow velocity in the pipe, the density of the fluid, viscosity of the fluid, a diameter of the pipe if you like, and the pressure gradient, dP/dL in this particular case, I think it was. So these could be combinations of variables. And so if we have 5 variables which describe behavior, and in these variables velocity is length over time, and density is mass per unit volume, if we have all 3 of these mass, length, and time components included, then 5 minus 3 are the number of dimensionless variables that would describe our system. And so Buckingham pi is just the recipe, if you like, by which we put together the dimensionless variables that describe our system. And I guess it's described here. I'm not sure whether we need to go through it. Oh, okay. So in this case, here are the kind of the same 5 variables. I guess D has been changed for B. So it has to be the same again, right? 5 variables, 1, 2, 3, 4, 5. Mass, length, and time are represented, so there must be 2 dimensionless groups come out of it. You take repeating variables, and in this particular case, the repeating variables are diameter, velocity, and density. And so when you make the pi variables, there are two other dependent variables that you'll get to use. One is going to be this, and the other one is going to be viscosity, right? Oh, where'd it go? Okay, let me get this then. It is this. Okay. Same stuff. I won't be able to write on this, but I'll describe it. So when you're using the pi groups, in this particular case, there are 3 repeating variables. The other groups would be delta p and mu. So in each term, you take each of those. In the first case, you take delta p, the repeating variables. You'd go through this recipe. I'm not going to go through it here unless you want me to be able to figure out what these components are. Basically, the idea says that we want a group that has no units in it. No units of mass, no excess units of mass, length, or time. And so the exponents that have to exist on this are 0, 0, and 0. And so when we take the repeating variables raised to some power a, b, or c that we'd like to figure out, and we take the dependent variable raised to the powers that we know are prescribed, then we want to be able to select a, b, and c so that we get this right-hand side. That's really all we're doing. And so we go through this little recipe here, solving 3 simultaneous equations to figure out what a, b, and c are. We apply a, b, and c to each of these terms, and we come up with a non-dimensional variable, uniquely defined by those 3 repeating variables and the dependent variable. Uniquely defined, always. And it will be defined for you, and there will be a question on this. So we've done that with the repeating variables, which was pressure drop. The other, dependent variable was viscosity. And so the next one is to substitute pressure drop for viscosity. Go through the same process. Most of this, I guess you've already realized this, right? Most of this expression stays the same. The A's, B's, and C's that you had up here, everything left to the right of this cursor, A, B's, and C's, is exactly the same as down here, right? So that doesn't change. The only thing that will change will be stuff in this left-hand column. And we're solving for the new values of those A, B's, and C's. Those will change, and that gives us a second variable. And so now you've got those 2 non-dimensional variables. What that tells you, if your system is controlled by 2 non-dimensional variables only, then you can write a graph that has variable 1 and variable 2 on that graph, and you'll have a single line that will represent it. So any experiment that you do will give you a data point. A second experiment you do, maybe at a larger velocity, will give you another data point. Together, all of those data points will make a single line. It doesn't have to be monotonic, it could be all over the place, but it'll give you a single line. If you have 3 non-dimensional variables, then you'll have the same behavior. You'll have a single graph, but now if you choose the 3rd variable to be a certain number, say you have Reynolds number, Euler number, and length to diameter ratio of the pipe. Length to diameter ratio is 1, length to diameter ratio is 2, length to diameter ratio is 3. So the 3rd pi term that you'd have would be L over D, and that would give you different curves for different L over D. If you have 4 pi terms, then you have a 4-dimensional graph. It gets a bit more complicated in terms of thought process then, but that's basically it. That's all dimensional analysis says. You're breaking it down to the minimum number of non-dimensional terms that will describe your system. Those terms are not unique, but if you're given the repeating variables and if you're given the dependent variables sequentially, then the dimensionless terms will be unique. We talked about geometric similitude, we talked about kinematic similitude, talked about dynamic similitude. We did some examples, I won't go through those. We've talked about the Bernoulli equation in its different forms and head losses. We've talked a bit that head losses in some respects are related to frictional characteristics along pipes and what forces we'd have to apply to resist those. And we haven't talked about this yet, but in this week we'll talk about this slide here and the Moody chart, which we kind of drew perhaps a not so fantastic version of. But again, we made the points that 2000 is this transition to turbulent, 4000, transition from laminar, 4000 is this transition to turbulent. Laminar flow behavior is not a function of roughness, but is a function of Reynolds number. Hence, this curve varies for a circular tube as a function of Reynolds number, but not as a function of roughness. And for turbulent flow, behavior varies with roughness. Very rough tubes, very smooth tubes. The envelope at the bottom here for all smooth tubes. And in the turbulent regime, it's a function of relative roughness. The friction factor is a function solely of relative roughness, but not of Reynolds number, because these curves are flat. And that's probably it. That's it. Yeah, the rest we talked about. We haven't covered this stuff, so you don't need it. But certainly we'll talk about, this week, we'll talk about some more flowing pipes, and that's more ammunition, I guess, to take with you.